In this video, we're going to work through some applications that involve nonlinear functions. The first example is going to look at a polynomial function. So gift cards have increased in popularity in recent years. The US sales of gift cards in billions of dollars after 2003 can be modeled by the function below. We want to graph the function using this window and then figure out what are the projected sales of gift cards in 2008. So the first thing that I'm going to do when I graph this is I'm going to go to y equals and enter in my function, which you could see on the graphing calculator that's displayed. Once I know that my function has been entered correctly into the y1, we then go to the window key and we can enter in our values. So remember that this first set of parentheses, negative 10, 10, and 1, referred to the x values, x min, x max, x scale. And the 0, 1, 20, 10 refer to the y values, the y min, the y max, and the y scale. Once I enter in those values, I leave everything else to whatever it defaults as, and then I click the graph key to see what this function looks like in this particular window. I'm now going to use the graph to figure out what the projected sales of gift cards in 2008. Well, since my function is in billions of dollars after 2003, that means that 2008 is going to be year 5. So if I go to second and then to the trace key, that brings up the calculate menu. And those are all the different functions that we can do using the graph. So the one that we want is option 1 for value. Now I'm going to set x equal to 5 since 2008 is 5 years after 2003. And we get our solution. So we can now write this as a complete sentence. The projected sales in 2008 are 103.395 billion. In the next example, we're going to look at a radical function. So weekly operating costs for an airline are given by the function given, which is in millions of dollars, where x is the number of passengers in thousands. So notice that my output is in millions, whereas my input is in thousands. So the first thing that we want to do is state a reasonable domain for the function. Remember that the domain is all possible x values. Well, we're talking about passengers on an airline. So you could really kind of be creative in what you make your passengers, but we know that we can't have negative passengers and we can't have infinite passengers. So one possible practical domain would be 0 to 100,000 passengers, or you could have 0 to 1,000,000 passengers. It really does not matter what the exact numbers are, as long as they kind of make sense in the problem. The next question asks us to estimate the weekly costs if there are 20,000 passengers that week. Well, if there's 20,000 passengers, that means the x value is equal to 20. So when I plug in 20 into my function, we could do that right into the calculator, we get that the weekly cost for 20,000 passengers is about $5.29 million. Lastly, we're asked to estimate the number of passengers in a week with a cost of $3 million. So I'm going to set my function equal to 3 since we already know that the output here is already in millions of dollars. We're going to solve this radical equation. Since it's a square root, we get rid of the square root by squaring both sides. That simplifies to be 4 plus 1.2x is equal to 9. And now we just have a linear equation to solve. Subtract the 4, divide by 1.2, and we get x is approximately 4.167. Now I stopped at 3 decimal places because we know that our input value is in thousands, and 3 decimal places is the thousandths place. So if I'm going to write the meaning of this number, well, that means that there are approximately 4,167 passengers in a week that has a cost of $3 million. In this example, we're going to look at a quadratic function. So manufacturer of water filters has a monthly cost of C of x, where x is the number of filters manufactured per month, and a revenue given by R of x. We're going to use the graph to find any break-even points. So again, in my calculator, we know that the break-even points are going to occur when the cost and the revenue are the same. Those are the 2 points where we have zero profit. So as you can see in y1, I'm going to put C of x, which is my cost function. In y2, I'm going to put my revenue function. And I'm going to enter in the window that I was given. Once I have everything entered, I can go to graph. And we see that we have 2 intersections. So I need to find those separately. Remember, to find intersections, we do second and then the trace key, and we want option number 5. So I'm going to do that for both of those break-even points that I see on the graph. Once I have both of those, I can then write my solution as a complete sentence. We see that there are 2 places where the cost and the revenue are equal, so that's where there's zero profit. So the cost and revenue are equal when 13,542 water filters and 66,458 water filters are manufactured and sold. In our next example, we're going to look at a rational function. A manufacturer of lawnmowers uses the function below to model the cost per lawnmower in dollars, where X is the number of lawnmowers produced. We want to write the average cost function, determine what the vertical and horizontal asymptotes are and if they have any practical meaning in this problem, and then find out what will the average cost be if only 300 lawnmowers produced, and what is the minimum number of lawnmowers that must be produced in order to have a cost of $199 per mower. So the first thing that we need to take care of is the average cost function. If we're taking the average of this cost function, think about what it is to take an average of a set of numbers. We would add up all the numbers and divide by how many numbers we have. In this case, we're talking about lawnmowers. So we would add up the total cost of a certain number of lawnmowers and then divide by the number of lawnmowers that we're looking at. So my average cost function is 132x plus 75,250, and that entire thing is divided by x. That will give me an average cost. Next, I want to talk about the vertical asymptote. So remember, the vertical asymptote is present when there are values that are not allowed in the domain. When we have fractions, we know that we can't have zeros in the denominator. So my denominator here is x. That means 0 cannot be in the denominator. X cannot equal 0. So that's my vertical asymptote. My vertical asymptote is x equals 0. And if we think about what does x represent the total number of lawnmowers. So if my function can't cross over x equals 0, well, that just means we always have to have a positive number of lawnmowers. So the number of lawnmowers must be greater than 0. In part C, we're asked to find the equation of the vertical asymptote. So the vertical asymptote can be found by looking at the leading coefficients of the numerator and the denominator when we have the same degree. Here we have a linear function on top of another linear function. They're both degree 1. The leading coefficient in the numerator is 132. The leading coefficient of the denominator is 1. So if I divide those, I get y equals 132. So that means in this problem, a of x is equal to 132. A of x, remember, represents the average cost per mower. So that means that the average cost per mower must be greater than $132. This should make sense if you think about what our cost function was It's 132 plus this flat rate of $75,250. Well, we know when you're running a business, you want to offset that by passing along those flat costs to the consumer. So if you have an average cost that's less than $132, that means you're eating up this flat fee of $75,000. You're going to end up losing money. In order to not lose money, you always have to make sure your average cost is going to be greater than $132. We're then asked, what is the average cost if we have 300 lawnmowers that are produced? So here we would plug in 300 for X, and we would get A of 300 is equal to 382.83. So that means the average cost per mower, if we produce 300 lawnmowers, it's about $382.83. Again, I rounded to 2 decimal places because we're talking about money here. Lastly, we're asked, what is the minimum number of lawnmowers that must be produced in order to cost $199 per mower? So here we're setting the average cost. We're setting A of X equal to 199. This is a proportion, so I could cross multiply. I get 199x is equal to 132x plus 75,250. And now it's just a linear equation. I'm going to subtract 132x from both sides. I get 67x is equal to 75,250. And then all I have to do is divide by 67. I get that we should produce about 1,123 mowers to have an average cost of $199 per mower. In our last question, we're looking at piecewise defined functions. So it's pretty easy to read the table and be able to determine how much a package is going to cost depending on the weight of the package. So if I have a package that is only 5 ounces, well, I know that falls into this line right here. We're not 8 ounces. It's a flat rate of $13.65. If I have a package weighing 2 pounds, so I'm over 8 ounces, up to 2 pounds, I would be in this line, $17.85. If I have a package that's 3.8 pounds, okay, that means, well, I'm over 3 pounds, but I'm not yet at 4 pounds. I'm right here, $24.20. So I want to use this information in the table to write a function. So this is really a very classic application of a step function. Our steps are represented by the weight of the package. Our rate gives us how high that step is. So we're going to let X be the weight of the package in pounds and P of X be the amount of postage in dollars. So if my value of X, if the weight of my package is less than 0.5, so again, the reason why we have 0.5 is we need to have a consistent unit with our weight. We can't have ounces and then shift to pounds. But we know 8 ounces is really a half a pound. So it's easy to just make everything in terms of pounds. So if X is less than or equal to a half a pound, we're going to pay $13.65. If we're between a half a pound or up to equal to 2 pounds, we're going to pay $17.85. If we're over 2 pounds but we're less than or equal to 3 pounds, we're going to pay $21.05. And you could see that same pattern for the rest of the function, up to 6 pounds.